Okay, so here's where we ended, sort of where we ended yesterday. We found the average rate of change with our function notation right here. Oops, don't want to do that. And then we were supposed to write the equation of the secant line with this slope that we found. I'm still on the eraser. Okay. With this slope that we found, I think we decided to use this point, and we found P. We had to go find P of 2, so it was 2, 8.5. Is that correct? Okay. And then when we write the equation of the line, you can get y minus 8.5 equals the slope, which is 2.35, times x minus 2. Now remember, we really want it in y equals. If you're a little shaky about writing the equation of the line, then I would write it in this form first. Eventually, I'm going to kind of skip this one and just go straight to this, 2.35 times x minus 2 plus 8.5. But again, if you're a little shaky, it's maybe better to start with this one because then they're both minus and you don't get the minus and the plus mixed up. I mean, it's kind of a preference there, okay? All right. So then it says, use the secant line to estimate the demand. So we're going to use, it says use the secant line, which is this is what we just found, to estimate the demand for 3,000 units. So although we used our calculator to find this number right here, and we did F1 of 2 to find that, right? That it is not asking us to find F1 of 3. It's asking us to use the line we just found to estimate it, okay? So if I do, well, this is not H, it is a P. So that means that P of 3, and it says to estimate it, is about, and then I'm just going to substitute a 3 into this line, 2.35 times 3 minus 1 plus 8.5. Now, if the 2.35 and the 8.5 were not exact decimals like we got, then we would have had to store them. And we'll get to all that stuff. Luckily here, these were nice, pretty decimals, so we're not going to have to stress out over that. But eventually we will do that, so we just got to make sure. Yes? Why did I put 1? That's a very good question. I wanted to see if y'all are paying attention. Good job. No wonder y'all are looking all confused over there. I was like, oh, Lord, why are they confused? Thank you. There you go. Probably because 3 minus 2 is 1, and my brain does that sometimes. But notice, when I substitute stuff in, and this is something I'll repeat a lot, first step is zero work, you just substitute it in. Because sometimes your careless mistakes are made when you were combining things while you substitute or whatever. You know, you're like, oh, well, that's easy. I can add this, add that. No, just leave it exactly like it is. All right? So we are going to use the calculator for this, though. So we go to the calculator. Now, because we did this yesterday, when you hit the on button and you have this black screen, you can hit 4 for current. And even if it doesn't take you to the graph screen, it should take you to this one where you probably have some stuff typed in, but mine's cleared off. Okay? We good with that? All right. That way, if we needed it again, we have it. So now we're just going to use the calculator as a calculator and say we have 2.35 times 3 minus 2. I'm pretty confident I know what 3 minus 2 is, but again, we're just going to be safe here. Plus, because that's where our careless mistakes happen, 8.5. And that's what we get, is 10.85. Okay? So we get 10.85, so that's equal 10.85. So it says to estimate the demand for 3,000 units. So 3,000 units, suppose the demand, okay. And now we have to decide, the next part is this an overestimate or an underestimate? Explain how you know. Here's what we are not doing. We are not finding the actual value for P of 3 but from our function and comparing the two. That's not what it's asking us to do. It's asking us to use our knowledge of the function itself. So when we look at the function, even though we only see a little bit of it, because of what we typed in, and we know it's quadratic, then we know it has to look like a parabola, right? So that tells me that even though all I see is this bottom part right here, that what I don't see doesn't have like a curve that comes back down or anything. Like I know that it's concave up the whole time is kind of what I'm getting at. All right, so knowing that, I'm going to draw myself a little Okay, here's this. It's not even going to be, I just know that that's what it looks like. That's what's happening, right? All right, so the function is concave up. And when I'm estimating the demand, now when I draw my picture, I'm not drawing it necessarily 100% accurate to what's in the graph, because nobody's looking at my pictures. My pictures are for me, okay? So on your pictures, if you just draw it where you can kind of make the picture make the most sense for you. So let's say that we know that we use the 2 points that our line was on, had an x value of, we had an x value of 2 and an x value of 4. Okay, so let's just say that the line goes through these 2 points. Okay, the line goes through those 2 points. That means this x value is 2, this x value is 4. You with me on that? When we use the equation of that line to come up with this number right here, we were estimating it at 3, which means the point is somewhere like right there on my green line. You with me on that? What I'm estimating is what the answer would be on my orange parabola, right? So is my purple point an overestimate or an underestimate? Is this number, my y value, going to be bigger or smaller than the actual value on the parabola? Bigger, right? Because it's above it, yes? So whatever that y value, so x value is 2 and 4 here, it's 3 here. This y value, which is 10.85, is bigger than whatever the actual y value is on the curve. Does that make sense? And that's because the secant line is above it. All right, were you with me on that? All right, so here's how you have to write this out. And there was a question very, very similar to this on the AP exam last year. And no matter how beautifully you wrote everything, if you left one little piece off, you didn't get credit for it. So we got to be careful we don't leave certain things off. Because some of you can use a whole lot of words and say a whole lot of stuff, but not actually say what's important, right? That might work in your English classes because you can get your word count up. You don't ever want to try to get your word count up in a math class because we don't want to read all that. All right, so here's what we do. We say, so we can say that this is an overestimate. Okay, so first I have answered the question. This is an overestimate, or I can say 10.85 is an overestimate, or the answer in part C, or whatever, is an overestimate because P is concave up so the secant line is above the curve. Now, let me ask you this. Is the secant line always above the curve? No. And here's the point we can't leave off, or the part we can't leave off for sure. P is concave up, so the secant line is above the curve on 2 to 4. Then let me ask you this. So remember, this x value is 2, this one's 4, so from 2 to 4, that's when the secant line's above it. We estimated it at 3, that's why it's an overestimate. If I use this line to estimate at 5, is that going to be an overestimate or an underestimate? An underestimate because it's below the curve on, from whatever, however you would say it. Does that make sense? Do you see how these little pictures that aren't necessarily 100% accurate can be very helpful to wrap your mind around what's going on? Okay? And let's say that it had been concave down and we did the same kind of thing, then it would have been an underestimate because it's below the curve from 2 to 4 or whatever. Okay? So just drawing that little thing, we don't care about exact values and how pretty it is, but it helps you visualize, is it above, below, what's happening, where's this point, and do whatever. They don't have to be gorgeous. Don't make it like a little ticks marks on your axes or anything like that. None of that's necessary. Okay? What questions you got? We all good? Beautiful. All right, flip it over. So now it says selected values for several functions are given in the tables below. For each of the tables of values, determine if the function can be linear, quadratic, or neither. Okay, so what we did with these earlier on the notes is we just straight up found all the rates of change. Okay? And that's fine, and that's going to be necessary. But one of the phrases I told you is very, very important. It says, over consecutive equal length input value intervals, right? So we need to check that, meaning I need to check my input value intervals here. So 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. 9 minus 7 is 2. So by checking that, guess what I've already found? The difference in the x's, which is what goes in the denominator of your slope, right? And again, we're not, so like, again, if I just say, what is the rate of change? Just like we did here, so let me remind you this. Like if I said, what is the rate of change? We write it, well, actually all three of these. We write it in function notation, then we put this in and we make it all formal so everybody understands where our stuff is coming from. On this one, I don't have to be all that formal because I just need to find them kind of for myself. So when I'm here, right, I'm going to find this rate of change. I know my denominator is already 2. I don't have to put the 3 minus 1 for myself. But then I do have negative 5 minus a negative 2, which gives me what? Negative 3 halves, right? Now let's do this one. I know 2 goes in the denominator, so that's negative 4 minus a negative 5. 1/2, positive 1/2, yes. And then here, 2 in the denominator, 1 minus a negative 4, it's 5/2. And then 2 in the denominator, 10 minus 1, 9/2. Okay. So we are trying to figure out linear, quadratic, or neither. Is it linear? No. Our rates of change are not constant, so it is not linear. So I need to see how my rates of change, right? So then I'm going to do the differences here. So 1/2 minus a negative 3/2 gives me 4/2, which is 2. 5/2 minus 1/2 gives me 4/2, which is 2. 9/2 minus 5/2 is 4/2, which is 2. So we have already decided that it is not linear. Is this quadratic? Yes. Okay, so here is how we answer this question. Remember, we say f is quadratic because average rates of change of f are constant. Now, earlier on the notes, we kind of stopped here because I knew it was already a lot of words, and I had said the words rates of change so many times that your brain was spinning. But we actually need to add a little bit of something on here. F is quadratic because average rates of change of f are constant over equal length inputs. All right, now, so this is the part here that I added over equal length inputs. Now, that you might be like, great, that's even more words. But remember what it actually says is over consecutive equal length input value intervals. That's a whole lot more words. We can condense it to this and it's perfectly fine, okay? So we're not having to write out every single word and make it sound formal. We just need to make sure we get the point across. Everybody good with that? Okay. We are going to skip this one because I moved things around and then that one didn't end up doing what I wanted it to do. So we're just going to skip that one. All right, so let's look at 3. So we're going to start with the differences here. This is 2, then 1, then 5, then 1. Now I don't have equal length input value intervals, but that doesn't mean that I'm done at this point, because for linear, you don't have to have that because you can pick any 2 points. Make sense? So I still have to check and see if it's linear. And if it's not linear, then I can't do anything else because they're not equal length. So here, on my first one, I know I can put 2 in the denominator because I already figured that out. 4 minus 0, that gives me 2. For the next one, 1 goes in the denominator. 6 minus 4 is 2. Next one, 5 goes in the denominator. 16 minus 6 is 2. Next one, 1 goes in the denominator. 18 minus 16, 2. Even if you feel like you see a pattern already, you got to find them all because the last one could be 5 or something. You never know. So is this linear? Yes, these are the average rates of change, and they are what? Constant. We don't have equal length intervals. It does not matter for a line. So then I can say that H is linear because average rates of change of H are constant. And I don't have to say anything about intervals even if they were because it's linear. Everybody okay with that? All right, now, there's more than one way to answer these questions. And I have seen, so they released some of the free response questions from the exam. They didn't release any of the multiple choice questions that they actually used on the exam. So we don't know exactly what was asked and how, but there's so many things you could do, and I don't know how much that would be helpful. But I've seen these questions on the multiple choice part answered different ways. And so we're going to look at 3 a little bit differently when we go through this because I want you to see the differences, and we'll talk about it. I mean, it's basically what you did in Algebra 1 is what it comes down to. But all right, so we're still going to look at differences here, right? And so 0.1, 0.1, 0.1. I have equal length input value intervals. And so if you recall, in Algebra 1, when you were trying to figure out, is this linear or quadratic, because those are the same things that you did, right? Take your headphones off, please, completely off. Then you just looked at differences. So I'm not going to actually find the rate of change here. I'm going to look at the differences. 1 minus 4 is negative 3. Negative 1 minus 1 is negative 2. Negative 2 minus a negative 1 is negative 1. If I had gotten the same number all 3 times, then I could say this is linear because the first differences are constant. Right? You can talk about the differences. That's not what happens here. So this one's not linear. I don't have the actual rate of change, but that's okay. It still wouldn't work out because notice I divide each one of these by the exact same number, so it still wouldn't work. So I'm going to find the second differences. Negative 2 minus a negative 3 is 1. Negative 1 minus a negative 2 is 1. My second differences are constant. I don't have the rates of change, but I have my second differences. So you could see this because this is more likely to be, this will be not always on a classroom test, okay? Classroom test, you're going to have to write some stuff out that you may not have to on the actual exam. But on the actual exam, these are multiple choice questions. And so your answer choices could either talk about rates of change, like we already saw, or it could talk about differences. I've seen both of them. So here, second differences are constant. That makes it quadratic. So first differences, if they were constant, it's linear. Second differences are constant. That makes it quadratic. If these weren't constant and we did third differences, I'd have to have more numbers, but it would be cubic and so forth and so on. So we can answer this question and say K is quadratic because second differences are constant. Again, I feel like I feel like these types of answers came from some of the earlier questions that they had given us, and then I think it's kind of evolved where they're all talking about rates of change, but it could be either way. And if you notice here, basically this is kind of like the second difference anyway. It's kind of the same thing, but you okay on that? So what I want on the assignment, I can't remember how many quadratics there are. Like, don't do it this way unless you've already done one where you talk about the rates of change, just so that we can, I think that that's going to be a little bit more important for us. Everybody okay on that? We good? All right, then we're just going to do 2 of these. We don't need to do all of these. We've got selected values for several functions are given in tables. This time we want to determine if it could be concave up, concave down, or neither. And remember, we're not doing this by graphing. Like we don't have a graph. I'm not going to plot these points to figure it out. I have to actually find my rates of change here. So again, I'm going to look at the input value intervals. It's all 2. That kind of helps me get started on my average rates of change over here. So 2 goes in the bottom, and then I'm going to have -6 minus a -10. So what's that going to be? 2. All right, then you go ahead and find the rest of them. Okay, what do you notice about the average rates of change? What is happening with them? They're not constant. Are they increasing or decreasing? Decreasing. Since they're decreasing, what does that tell us about this function? Concave down, exactly. So we're going to answer the question. Q is concave down because average rates of change of Q, I got to say it again, not just any average rates of change, right? So Q is concave down because average rates of change of Q are decreasing over equal length inputs. What questions you got? Good on that one? And again, I added that equal length inputs, which wasn't on one of the other questions that we had done. All right, so let's do 8. See, this is 1, and then 1, and then 1, and then 1. So that makes it nice. So since they're all over 1, it's really just 5 minus 8, which is -3. And then 2 minus 5, which is -3, -1 minus 2, which is -3, and -4 minus a -1, which is -3. Okay, since the denominators would all be 1, I didn't even have to worry about them. So what can you tell me about my average rates of change? Constant, okay? So that means that Q is what? Neither one, right? So S is not concave up or down because average rates of change are constant. And because they're constant, I don't have to say anything about equal length input values. I can because it's true, but I mean, it doesn't matter. What questions do you have? Anything? All right. So we're not going to do 9 just because I think we've done enough. Go ahead and get this taped in if you haven't already.